All right, welcome everyone to the TAP colloquium. Can I actually take a quick poll? How many people got the TAP email? And how many people got the All Steward email? And how many people only got the All Steward? Like you didn't see TAP, but you saw it on All Steward? And how about LPL? How many people saw it on only the LPL? Or maybe Steward and LPL? Okay, so there's still some. If you're not receiving TAP emails, please let us know so we can get you on the list, because I've heard from a few people, and you want to receive. I'm guessing if you're here, you want to receive. Okay, thanks. All right, so it's a pleasure to introduce Cristiano Longarini. He did his PhD in Milan, and he's now a postdoc at the University of Cambridge, a place that maybe you have heard of in passing. But we're very happy to have him here. He's been here for the past week, and he'll be here for the remainder of the week. So if you're interested in something he says today, and you want to follow up with him, you can find him in N327. And I think as many of you also know, he's going to be offering a computational workshop tomorrow starting at 11 on the code that has been used to produce many of the beautiful movies you're about to see. And if that's not advertising enough, there is also free lunch if you register. So please register so that we can provide you food. There's going to be like a little break during the middle of it so you can eat and ask him more questions. All right, and with that, I'll leave it to Cristiano.
Thank you very much for introducing me.
You can send this around in case you have it.
Thank you very much, and thank you for being here. Really excited about visiting here Tucson, and also really happy to talk about my work, the work I've been doing during the last few years. And so my topic of research is protoplanetary disks and planet formation, and I'm mostly interested in the role of self-gravity and gravitational instability in protoplanetary disks. If you have questions, if you don't understand something, you can just interrupt me during the talk. I'm happy to. Okay, so first of all, I would like to point out that self-gravity is fundamental in astrophysics, and it is important at very different scales. Indeed, starting from planets and going to planetary rings, self-gravity really determines the structure and the characteristics of systems. Of course, self-gravity is also determining the structure of a star. It can be very important for protoplanetary disks, that is the topic of this talk. And then going to larger scales, it determines, for example, the formation of stars during the lapse of molecular cloud cores. It is fundamental in determining the structure and the dynamics of galaxies. Oh,
sorry.
Yeah. It's better. Okay. Yeah. Okay. And finally, it's also very important, like in cosmological scenarios of large-scale structure in the universe. Okay, so why do we study protoplanetary disks? So protoplanetary disks are very interesting astrophysical objects since they are the link between stars and planets. Indeed, they naturally form during the star formation process around the young stars, and they are the environment where planet formation takes place. In these simulations performed with an SPH code by Matthew Bate, I'm showing you the collapse of a molecular cloud core, and the white dots are the new form protostars. And as you can see, around the protostars, the material is is structured as a disk around these protostars. And so you can really see that these disk structures, the accretion structures around young stars, are really a natural consequence of the star formation process. And here you can see, for example, zoom in on different protostars, you can see different morphologies and different characteristics of this system. And nowadays, thanks to ALMA, we are able to observe protoplanetary disks with an incredible spatial resolution. So ALMA is a radio interferometer in the Atacama Desert in Chile, and thanks to ALMA, we can observe emission of gas and dust in these protoplanetary disks. For example, this is a very famous observation of the dust emission, millimetric dust emission, settled in the mid-plane around the star HL Tau. And while here, for example, I'm showing you emission of gas in this case, and you can see that the gas and the dust are tracing different regions of the disk, and they have different spatial extent. And so by combining the information from gas and dust, we can really have an idea of the physical processes happening in these disks that are the ones that are forming planets. And what is very interesting when we look at protoplanetary disks with enough spatial resolution is that they are not boring at all. They are not flat disks, but all of them show a lot of substructures. So this is, for example, dust emission from a sample of protoplanetary disks observed at very high spatial resolution. So you can see structures as spirals, gaps, rings, non-axisymmetric features. And of course, the main question is what are the physical mechanisms that are, physical processes that are creating these substructures in protoplanetary disks? And there are many explanations, there are many phenomena that can generate these substructures, but a common explanation is the presence of an embedded protoplanet. And actually, we have indirect and direct evidence of the presence of embedded protoplanets in these systems. For example, we can infer the presence of a protoplanet with hydrodynamical modeling, for example, the interaction between the planet and the gas and dust in the disk, and then compare it with observations, as in the case of, for example, Tau by Benedetta Veronesi in 2020. But also it's possible to indirectly probe the interaction, the perturbation of the protoplanet onto the surrounding gas by observing the so-called kinematic signatures of planet-disk interactions, as observed in, for example, these two cases. But it's also possible to, for just a couple of cases, to directly image the protoplanets or the circumplanetary material. And for example, the very famous case of PDS 70, where the protoplanet is very clear in this dust continuum observation. And let's say, under the interpretation that the substructures are created by protoplanets, this means that basically all the protoplanetary disks we are observing have embedded protoplanet. And so the process of planet formation must be very efficient and must happen early in the disk lifetime, when these protoplanetary disks are still young. And young protoplanetary disks are more complicated, but also, I think, more interesting. So when we observe young protostellar disks, we still see evidence of planet formation, where with evidence I mean substructures in gas or dust. These systems are strongly interacting with the environment also. For example, these two cases, you can see that they interact with the protostellar environment. So, for example, with the surrounding stars, or with the molecular envelope with infalling events of mass. And in general, and this I think makes sense, since protoplanetary disks are accretion disks, when young disks are more massive compared to more evolved disks. And this is also like an observational evidence when we observe like plots like this, where I'm showing the cumulative mass function of protoplanetary disks in different star-forming regions for different ages. And you see that younger ages younger regions contain more massive protoplanetary disks. And when protoplanetary disks are massive, the role of their self-gravity becomes dynamically important. And so the main question of my work is to understand what are the consequences of self-gravity and potentially gravitational instability in protoplanetary disks and in planet formation. So just want to point out a bit better what I mean with self-gravity and gravitational instability. So self-gravity basically is just a protoplanetary disk, let's say, is self-gravitating whenever the contribution of its mass to the gravitational potential becomes dynamically important. And just to give you an order of magnitude, this happens whenever the disk to star mass ratio, so the ratio between the disk mass and the star mass, is of the order of 5% or higher. And the self-gravity has consequences on disk structure. For example, the hydrostatic equilibrium and the centrifugal balance of a disk change when we take into account the self-gravity, because we take into account an additional contribution to the potential. And for example, it's very interesting to look at the consequences in terms of centrifugal balance. for example, if we plot the rotation curve of protoplanetary disk with different disk masses, we see that the velocity becomes super Keplerian, and this contribution is proportional to the disk mass. And this is due to the fact that a particle orbiting in a massive disk does not feel just the gravity of the star, but also the gravity of the disk, that the mass of the disk is enclosed in its orbit. And we've been working quite a lot on this topic, so like trying to estimate protoplanetary disk masses by measuring this contribution to the rotation curve. I won't go into the detail of this, but what we found is that for the brightest and biggest disk in the sky, that are, let's say, the best candidates because we can resolve them very well, we find that actually their disk-to-star mass ratios are pretty high, so are, let's say, higher. A part of them is higher than the 5%. So for the brightest case, for the brightest disk in the sky, that are also the most studied one, the effect of self-gravity must need to be taken into account, and not always this has been done in the past. And then, so this was self-gravity, but when a disk is massive enough, it can become also gravitationally unstable. So gravitational instability is an hydrodynamical instabilities, and which occurs in self-gravitating systems, and this is the dispersion relation for this instability that many of you know very, very well here. And it's possible to understand what is the instability threshold for this instability, and basically it can be described in terms of this dimensionless parameter called the Tumri Q parameter. This parameter is proportional to the sound speed and inversely proportional to the disk mass. And this means basically that hot disks tend to be more stable because the pressure contribution is higher, so that tends to stabilize the disks. And more massive disks tend to be more unstable, of course, because the mass, the surface density is related to the mass, so to the self-gravitating contribution. And so basically, hot and light disks are stable, cold and massive disks are unstable. And what are the consequences of gravitational instability? So when a disk is gravitationally unstable, it develops a spiral structure, which can be observed, for example, in this beautiful observation of dust continuum emission in these disks. And basically, you can see these spirals that are spiral density waves. So what this actually is,
Kappa,
yeah,
in the previous slide.
Oh, yeah, sorry, I should have mentioned. So kappa is called the epicyclic frequency, and it's in a Keplerian disk is just the angular Keplerian velocity, and this is a stabilizing term since it has a positive sign, because basically it's the rotation of the disk tends to support the disk against the collapse. Okay, so spiral density waves. So what are spiral density waves? So spiral density waves are not material waves, meaning that the particles, let's say, that form the spiral change as a function of time. It's not a rigid spiral rotating, but it's a consequence of a collective motion of particles. And I think this is very clear when we look at videos like this. So I think this is a good way to explain what is a spiral density wave. So you see the people forming the wave are not the same. They change as a function of time since the pattern is moving. And this is like these are the foundations, for example, of the spiral density waves. This is a theory that explains the structure and the dynamics of spiral galaxies. So, okay, so I told you that cold and massive disks can be gravitationally unstable. And now I would like to discuss a bit how we can reach this gravitationally unstable state. So what are the different paths to reach gravitational instability? So we start with a disk that is stable, so with a Tumri parameter higher than 1. And now we follow the first path to instability, so we play with the temperature of the disk. So we start cooling the disk with a given prescription. You can decide whatever prescription, can be radiative cooling, external cooling, whatever you want. And so since the disk is cooling, the sound speed is decreasing, and so the Tumri parameter is decreasing as well. And at some point, Q reaches the threshold equal 1, and the spiral structure develops. And what happens is that the spiral structure moves at a supersonic speed and starts heating the disk with shocks. And whenever there is a balance between the cooling and the heating from the spirals, we are in a self-regulated regime, meaning that the amplitude of the spiral perturbations remains constant with time. And we have this spiral pattern moving. But what can happen is that we are cooling too fast the disk, so the heating provided by the spirals is not enough to balance it. And so what happens is basically a runaway situation where the spiral density waves becomes, their amplitude becomes bigger and bigger, and at some point they just form gravitationally bound objects and they fragment. So this is the fragmentation limit when the cooling is too fast. But we can do the same, but playing on with the mass of the disk in this case. So we start with our stable disk and we start injecting mass with a given mass injection rate. And what happens is that at some point the mass of the disk is high enough to reach the Q equal 1 threshold. Spiral structure develops, and what happens is that the spirals are transporting the material that is injected onto the stars, and part of it stays on the disk. And whenever there is a balance between the injected mass and the one that is accreted from the star, we are in a self-regulated condition as before. But what can happen is also that we are injecting too much mass, so that the disk cannot sustain this and cannot transport it efficiently. And so we have in this, and the same way we can have a fragmentation case. And this is very clear when you observe hydrodynamical simulations. So this is an example of a self-regulated GI disks. You see the spiral structure has a fixed amplitude and it keeps moving in the disk. While here we will observe a fragmentation. So in this case, this is a cooling-driven GI simulation, and you see that a gravitationally bound object forms because the disk is cooling too fast. And yes, so I'm mostly interested in the first regime, so in the regime where the disk is not fragmenting, so when the disk is reaches this self-regulated state. Why? Because this is very interesting in terms of transport of angular momentum, which is a big problem in protoplanetary disks. Indeed, protoplanetary disks, as I told you, are accretion disks, and in order to transport the material from the disk onto the star, we need a mechanism that is allowing it, and we usually say that there is a viscous-like mechanism acting in the disk. It's possible to write, for example, a viscous torque, starting from basically assuming that there is a torque because the two annuli in the disk have two different azimuthal velocities, since they are basically Keplerian disks, and so the shear between these two annuli is creating this viscosity. But the viscosity then is described by mu, that is the kinematic viscosity coefficient, and but honestly, we don't know what is physically causing the viscosity. Because if one wants, for example, if one assumes that the viscosity is just molecular collisional viscosity, the values of nu are not high enough to explain the accretion we observe. And so what we say is that just nu is proportional to this dimensionless parameter called alpha. We call it alpha viscosity. And basically, this coefficient determines the efficiency of angular momentum transport. This is not a viscosity theory. I always say that this is just measuring how ignorant we are about the source of the viscosity. But what's interesting is that in massive disks, in gravitationally unstable disks, the spiral waves can transport angular momentum, and in a limit they can act as an alpha viscosity, so as a local transport of angular momentum. And in particular, this transport can be described with an alpha prescription whenever the disk to star mass ratio is low enough, where for low enough I mean not of the order of 1, which makes sense in a protoplanetary disk because we don't expect the disk to be as massive as a star. And this is clear, let's say, mathematically speaking, if we look at the energy of the spiral wave per unit surface. So it's composed by two terms. The first term is a global term, so it's a non-viscous term, which can be neglected when the distance-to-mass ratio is not close to 1. And so we have just the second term, which is a local transport of angular momentum. So it's really a viscous-like term. And what's interesting is that we can then define this alpha GI, so the alpha generated by gravitational instability, and is proportional to the delta sigma over sigma to the power of 2, so to the density contrast of the spiral. So if the amplitude of a spiral is bigger, then also the transport of angular momentum is higher, it's more efficient. And yeah, so now, as you see in this slide, I want to talk a little bit about gas kinematics. And maybe you were wondering why, but because a way to quantify the angular momentum transported with gravitational instability can be from gas kinematics. So the kinematics of protoplanetary, what is kinematics? It's basically the study of the velocity field in protoplanetary disks. And we can measure velocity fields very precisely with ALMA because we can map the Doppler shift of gas emission in these disks, spatially resolving the emission on the disk. And so basically, we measure this quantity that is the observed velocity field that is a combination of different velocity components that we then have to disentangle to understand what's going on. Here, I wrote just a couple of equations to just have a feeling of what kind of velocities are we talking about. And I mean, in protoplanetary disks, the main velocity is the Keplerian one, so the one generated by the central star. And this velocity is of the order of kilometers per second. So we are talking about this order of magnitude of velocity, so kilometers per second. And yes, so this is the main motion, but on the top of like a disk that is rotating with a Keplerian pattern, we can observe this so-called non-Keplerian kinematic signatures. So these are perturbations to the velocity field generated by different things going on in the disk. For example, if there is an embedded protoplanet, we expect to observe deviations from a simple Keplerian rotation. If we have like multiple systems, so if we have, for example, a central binary, this motion will be perturbed in the vicinity of the inner edge. And also the velocity field is perturbed whenever we have hydrodynamical instabilities, for example, gravitational instability. And this is what I am interested in. And in particular, in 2020, Cassandra Hall studied the kinematic signatures of gravitational instability. So through hydrodynamical simulations, then post-processed with a radiative transfer code, she found that GI leaves clear kinematic signatures in the velocity field of protoplanetary disks. These signatures are visible with ALMA, and basically they are called the GI wiggles because you can see they are perturbing the disk in this wiggling way. And of course, the position of this perturbation is related to the position and to the characteristics of the spirals. So what we did then was to study this problem under an analytical perspective. So in the linear case, for a self-regulated disk, we obtained the radial and azimuthal component of the velocity field, the one generated by the spiral density wave. And you can see that under the hypothesis of self-regulation, these components are proportional to square root of alpha. So the idea is that if the spiral amplitude is bigger, the transport of angular momentum is more efficient, and also the velocity perturbations are bigger. And so we thought that this could be, let's say, a way to probe the amount of angular momentum that is transported with gravitational instability. But as you can see here, there is another important scaling, that is the scaling with the disk-to-star mass ratio. You see these parameters are degenerate here, so which means that in order to probe alpha, we need to know the disk mass. And here I would just like to show you how a velocity field changes when we have a spiral on top of it. So this is a Keplerian velocity field, so unperturbed, and here I'm focusing my attention on this central channel of velocity. This is simply a straight line in a Keplerian case. And now what I'm going to do is to increase the disk to star mass ratio of this disk. And you see the velocity field becomes globally perturbed, and this channel shows this oscillation. And the same happens whenever we increase alpha. So if we increase alpha, we observe the same thing. So the idea is that these two parameters are degenerate, and so we want really to know the disk mass in order to understand the amount of angular momentum transported by these disks. So now I'm going to show you a comparison with simulations. So this is the analytical model, and we benchmarked it with hydrodynamical simulations performed with this code Phantom. It's an SPH code, and let's say we found a good agreement. Here I'm just showing you the image. We also quantified the level of agreement, and the agreement is pretty good, meaning that the linear theory here is working very well, which is good. And then, so we decided to compare this with observations. So the first disk we studied was Elias 227. So this is a very famous disk. It's been observed. It's one of the first disks observed with ALMA with a high resolution. And you can see here, this is thus continuum emission of this disk. And you see these two beautiful spiral arms. And a lot of people in the past thought that they may have been generated by gravitational instability. And but what was missing was a disk mass measurement, because without a disk mass measurement, we cannot be sure that this is gravitationally unstable. So in 2021, Benetta Veronesi was able to estimate the disk mass for this system with the rotation curve method I talked about before. And they found that the disk to star mass ratio is of the order of 17%, which is, let's say, in the self-gravitating regime for sure. And so it's very likely that this disk is really gravitationally unstable. So this is the velocity field as proved by a molecule called 13CO with ALMA. And you see that there are these global perturbations that which shapes seems the wiggle I showed you before. And they are also collocated with the continuum spiral. And so what we did was to apply our analytical model. And since we know the disk mass, we could constrain alpha. And the value we found is 0.038. Okay, this is very, very interesting, but I mean, this value itself doesn't tell us much. I mean, what does it mean, 0.038? And so what we did was to try to connect this to something we can measure, to have an idea of the magnitude of this. And so with like simple viscous theories, it is possible to relate alpha to the accretion rate into the central star. So the accretion rate is a quantity that can be measured with observationally speaking. So it's and then we have, let's say, all the information of the disk to do so. So we did it, and we compared it with the measured value. So the value we estimate is 10 to the minus 6.9 solar masses per year against the measured one that is 10 to the minus 7.2 solar masses per year, which is like in a good agreement within the error bar. I think it's in a good agreement. Of course, this equation has a huge hypothesis that is that the outer disk is connected with the inner one. So the angular momentum transported from the outer disk is then also transported to the stars. So there's nothing in between. So there are no like other mechanisms regulating the actual accretion to the star, which is a huge hypothesis. But I mean, it seems to work. So what we can say is that gravitational instability is, let's say, providing the angular momentum transport that is enough angular momentum transport to explain the accretion onto the star. Yes.
For Elias 227, are there measurements of accretion variability as well?
So we checked if the accretion rate was varying. It varied not much. It was always within the error bars, but there are not many measurements. So there are just, I think, 2 data points, which is not really helpful. Yeah. Okay. And the second case is Abiorighe. So Abiorighe is another famous protoplanetary disk, and this is an image of scattered light emission. So this is emission scattered from small dust grains disk, and you can see here that shows this beautiful spiral pattern. In 2021, with Robin Dong and Jess Speedy at the University of Victoria in Canada, we wrote an ALMA proposal to study the kinematics of this disk, because also this disk was, people thought it could be gravitationally unstable as well. And so we got time, and these are the data. So the data were beautiful and way more like difficult to interpret than we expected. So here I'm showing you the emission of 13CO. So this is the kinematics. And you see also here that the disk is like globally perturbed, and you can really see this oscillation here, which really seems the GI wiggle. And in this plot, I'm showing you basically the residuals of this velocity field. So this is the same velocity field, but with a axisymmetric Keplerian velocity field subtracted to it. And you can really see that there are these residuals that are following the shapes of the position of the spirals in scattered light. But the problem for this disk is that we don't have a good mass estimate, and mostly because the disk is really it's too non-axisymmetric, so it's very difficult to use the standard models we have now for this. And also it's pretty face-on, so because of projection effects, we are losing some information. So what we could do is just to give like a curve in the disk to star mass ratio alpha viscosity space where the disk lies. So basically these are in this curve you can find the two values, one of viscosity and one of disk to star mass ratio, which are reproducing the amplitude of the velocity perturbation we are observing. Here, for example, for the 13CO, we are showing with yellow the observed velocity field in the central channel, and with gray our analytical model. And I mean, we just have a curve, we don't have actual values, but I mean, we can like think that the alpha viscosity should be, let's say, higher than 10 to the -2, lower than 1 for sure. So let's say we have like a confidence range for these values, but I think that more work needs to be done for this. But if we look again at a biorig, so this is, as I told you, is the dust scattered light emission, so emission from small dust grains. If we look at the gas, this is gas emission. So the scale, you need to scale, you don't need to scale. So the gas emission is, the extent is way bigger compared to the scattered light. So here we are talking about like a radius of the order of 1,000 of astronomical units. And you see that the emission here, it doesn't not just come from the disk, it also comes from the environment, probably from a molecular envelope that is feeding the disk. And if we even zoom out, we see that a biorig is inside this molecular complex in a very crowded region of the molecular. So here the effect of the environments are fundamental. And so what is likely to that is happening is that gravitational instability here is triggered by infall rather than by cooling. And we have actually evidence of infall happening in this disk. This is a work by Jess Speedy earlier this year. So she could disentangle the emission coming from the disk and coming from not the disk, that is in this case the envelope. She could trace some streams of material from the cloud to the disk, and they're hitting the disk in a given zone called the merging zone. But interestingly, if you look at this other molecule, SO, this molecule is interesting because it is a very good shock tracers. We observe that in the merging zone, there is a shock, which is likely due to the fact that the material is hitting the disk and it's shocking the material. So here, infall is happening in this disk. And so I think it's worth spending more attention on infall-driven gravitational instability. And so let's go a little bit back on self-regulation. So I want to show you a bit more about self-regulation in the case of infall. But let's go back to the cooling case. So this, as I showed you before, is a simulation with self-regulation and cooling. What are the characteristics of this self-regulated state? First of all, the two-meter parameter Q is constant equal 1 throughout the disk. This is the first, let's say, self-regulation condition. And then, as I told you before, here we have that the cooling rate is balanced by the heating rate. And so basically the disk here is acting as a thermostat. So whenever this cools too much, then the spirals are heating it back, reaching this self-regulated state. And in this case, the amplitude of the perturbation is given by basically the cooling. But if we look at cooling, self-regulation with cooling, actually things are not as easy as I told you. So because in the case I showed you before, we are completely neglecting any source of heating, of external heating. For example, irradiation from the central star that we know is very important in protoplanetary disks. And these are, for example, simulations performed by Sal Rother in Leicester. He performed these simulations coupling the hydrodynamics with phantom with the radiative transfer with the call code MC Fost, and studying the evolution of massive disks. And so what he found is that since the disk is irradiated by the central object, the gravitational instability tries to kick in, but is not able because the heating from the central object is too strong and is basically erasing the gravitational instability. And this has also been suggested by a PhD student in Cambridge, Kat Leedham, where she studied this problem, but in local simulations, and she found basically that for a high level of irradiation, the transport of angular momentum goes to 0, meaning that gravitational instability is not really acting here. And so what about self-regulation with info? So as I told you before, it is that we have a disk, we are injecting mass, spiral structure develops, and what happens is that part of the mass that is injected is transported onto the central star, and part of the mass is just feeding the outer disk, increasing its size and its mass. And what are the, let's say, the characteristics of this self-regulated state? We can understand them like very easily with these two equations. So the first one is the continuity equation. So we basically say that the rate, so this is the stellar accretion rate, and this is, let's call it disk accretion rate. So the derivative of the disk mass as a function of time, they're equal to the injection rate because of the conservation of mass. And also we want that the disk is in self-regulation. So we want that the two-meter parameter is stationary with time, so that it doesn't change with time. And this translates into this condition, because basically in an isothermal disk, we can say that the two-meter parameter is proportional to the disk to star mass ratio. So basically these two equations combined give us these two results. So the stellar accretion rate and the disk accretion rate are related to the injection rate in this way, where Q here is the disk to star mass ratio, which is a constant in this case because of this equation. So the idea is that the evolution will bring the disk to have a constant disk to star mass ratio as a function of time. So of course, this is a very, very simple, let's say, argument for isothermal disks. So what we did was to try to test it, for example, with the 1D models. So we solved this equation. This is the diffusion equation for the surface density for protoplanetary disk, under the hypothesis that the disk is locally isothermal, so that the sound speed is basically not evolving with time. And in this equation, what appears is nu, so the viscosity. Here we prescribe the viscosity in a way that is basically mimicking the effect of gravitational instability. So the viscosity activates only when Q is of the order of 1, so when the disk is unstable. And then we add this injection term, which is basically describing how the surface density changes as a function of time because of the injection of material. And here, to start, we chose a very, very simple injection profile. So we are basically injecting mass at a given radius at a fixed rate as a function of time. and the velocity of the injected material is matching exactly the velocity of the disk there. So basically, we're injecting in a ring with the particles that are appearing in a ring with the right velocity. I think this is very simplistic approach, but I think it's very good to start with this to understand what's going on, and then we can possibly make the situation more complicated. And so these are results of this evolution code. For example, this is surface density as a function of radius for different times. You see that the mass of the disk is increasing because surface density is increasing, and also the disk is spreading because part of the mass is like stored in the outer disk. And this is how the tumuli parameter changes as a function of time. So it's pretty much constant, meaning that we are in a self-regulated state. And so we also looked at the evolution of the global quantities, such as star mass, disk mass, and disk to star mass ratio. This plot shows this. So we have star mass and disk mass that are increasing with time, while the disk to star mass ratio is pretty much constant. And if we look at the derivative of these quantities, we see that they match very well with the expected values from our simple calculations. And so, since this worked in 1D, we decided to go to 3D simulations and see what happens. So this is a collection of three-dimensional simulations performed with the hydrodynamical code Phantom. This is an SPH code, so a particle-based code. If you want to learn more about the code, you can come tomorrow to the computational workshop. And you see, well, you see spiral patterns in these snapshots. And here I am comparing the results of the simulations, the 3D simulations, that are the dotted lines, with the 1D simulation, the solid lines, for the evolution of the global quantities. And we see that they match surprisingly well. And so, which means that the self-regulation, probably we understood how self-regulation works in this very simple case where we have an ideal injection procedure, the disk is isothermal, and the disk is isothermal. And then, okay, so what we asked ourselves was what are the differences, if there are any differences, between cooling-driven GI disks and infall-driven GI disks. And here I'm showing you simulations of two disks, one where gravitational instability is triggered by cooling, one by infall, and let's say that the speed of the video is different. So, I mean, you can compare like snapshot by snapshot, but it's worth comparing the morphology in these two cases. So what we see is that for the cooling case, the spiral structure seems, say, messier, you can say that. So the idea is that for the cooling case, we have that this spiral generates, but it's not like a clean spiral. There is not a single dominant mode, but it seems that there is a superposition of different modes. And also the spiral seems to create, then the material of the spiral is shocking, and then it destroys and it creates again and again. Well, for the infall case, the spiral structure seems cleaner. So there is a clear dominant mode and not much power on different modes. We can actually quantify this if we study, for example, the power spectrum of these two spirals at a given radius in the disk. So here I'm comparing two disks with the same disk to star mass ratio, which is a fair comparison when we study the morphology, because basically the morphology of a GI disk is determined by this quantity, so by the disk to star mass ratio. So for the same disk to star mass ratio, we have that the dominant mode is an m equal 2 for the infall and also for the cooling case. So the dominant mode is consistent, and I mean, this was expected. But what is different is the power that is in higher M modes. You see that here we have a sharp decrease of the power at different modes, while here we have still a lot of power on different modes, meaning that we have a superposition of higher M modes. And this is, I think, the first difference first big difference between infall and cooling. But of course, this may just be, let's say, numerically driven by the fact that we are injecting mass at a given location with like a given angular momentum, a fixed angular momentum in the disk. This is as if we are basically ringing a bell at the same frequency. And so basically what we also did was to study the pattern speed of this spiral. So for the infall case that is the left here, we tracked the spiral arms as a function of time, and we found that the spiral pattern speed is constant as a function of radius, meaning that we have a fixed pattern speed that is just rigidly rotating in the disk. While if we study, for example, a cooling-driven GI disk, this is a work from a bachelor student in Cambridge. He tracked the spirals for a cooling-driven case, and here I would like to say that the situation here is more difficult. Since we don't have a clear mode, it's more difficult to trace a single spiral arm, and also the spiral arms are not long-lived. They are destroyed and created again, but let's say within a time interval in which we could follow a spiral arms, it seems that the pattern speed is proportional to the Keplerian speed, which is a bit weird because, I mean, in this case, we expect that the inner part of the spiral should rotate faster than the outer part, meaning that the spiral will wind up very fast and disappear. But this is due to the fact that the spiral is not long-lived. So this is like the instantaneous pattern speed, but then what happens is that that spiral will disappear and reappear again. And so, I mean, the situation is more complicated, but we see like a quantitative difference here. And yeah, so what are the next steps? No, sorry, not next steps. Still want to show you something else before. Okay, so since we have a constant pattern speed in this simulation, there are three important locations in the disk that are the co-rotation resonance, the inner and the outer Lie blood resonance. So the co-rotation resonance is a location in the disk where the pattern speed is moving as the disk, so the same speed. And the inner and outer Lie blood resonance, there are two resonant locations where basically the spiral is say, kicking the material in that radius with like in a resonant way. And these locations are important whenever we study propagation of waves in disks. And in particular, in our simulation, we found something a bit strange. So this is a snapshot of the divergence of the velocity, which is basically just a spiral arm tracer. It's a very good spiral arm tracers in the R phi space. And you see that there is an inner spiral that basically interrupts close to co-rotation. Then there is this zone where we don't have propagation of waves, and then the wave starts propagating again outside of the outer Lie blood resonance. So what we did was to start from this simple equation and study the propagation of waves according to this relationship. And if we input the parameters of our simulation, we found that actually in the region between co-rotation and the outer Lie blood resonance, the wave number of this spiral wave is imaginary, meaning that the wave is evanescent, so it can't propagate here. And we proved this, let's say, analytically. So we found this region where the wave is evanescent that is really matching what we are also observing. So this is like another proof that sometimes the simple linear theory may be helpful. And yes, so as I was telling before, so what are the next steps for this work? So I think that the biggest concern we have is the injection procedure here, because as I told you, we are really injecting particles just in a ring without any difference of speed, and basically with this delta function profile. And so what we are doing now is to try to spread the injection region as a Gaussian. And interesting, what we see is that if we spread the Gaussian enough, a disk that normally would not fragment is fragmenting. And this is a bit strange. We are still trying to understand what's going on here. Probably, I mean, an idea is that for a disk, it's more difficult to transport angular momentum from the outer disk compared to the inner disk. And so since here we are injecting particles also more like in the outer part of the disk, not just at a given location, maybe the disk is not able to sustain this, and then self-regulation cannot occur. But we are still trying to understand what's going on here. And finally, this is like a another thing I've done recently. So this is I will show you a very low resolution simulation. I just ran this on my laptop as a test, where I tried to model a realistic injection, so like injection of particle as like in a streamer-like way, as in the Abia-Auriga case I showed you. So here I'm basically injecting particles like in a parabolic orbit from a given location, and this is a let's say inclined view, and this is an edge-on view. So you see that the mass of the disk is increasing, and it develops a spiral. And also, what is interesting here, since I am adding particles with a given inclination, we are also inducing a warp in the disk, and so basically we are like a new degree of freedom, which is inclination of the injection. And yeah, I think that with this I said what I wanted to show you today, and thank you very much for being here, and I'm happy to take questions.
Thanks, Cristiano. Questions?
I have one that is probably very trivial, but when you were showing the dust emission and the gas emission, and you showed that the gas emission was way more extended.
Yes.
One thing that caught my eye is that the dust emission was not only less extended, but also closer to the inner star here.
Yes. Yeah.
And I don't know, intuitively I would have expected the opposite, because I'm used to think about massive star with lots of UV radiation that destroys the gas. So is my intuition off just because of that?
No. So in this case, so here we are not talking about massive stars. So these are Titori stars usually. And it is that the dust is more concentrated closer to the star because of radial drift. So this is like an effect of the aerodynamical coupling between gas and dust, which makes dust particles to migrate inwards because of the coupling with the gas.
So it is expected to find more dust closer to stars.
Yes. And here I'm showing you small dust particles, which are very well coupled with the gas. So they do not experience a strong radial drift. But if I showed here, I don't have the image here, sorry, but like bigger dust particles, which are like a stronger radial drift, you would see that they are basically just in this very inner region. Yeah.
And so the accretion shock on the Titori star does not produce radiation. It's hard enough to destroy that, clearly.
Yeah.
Thank you.
But I think, I mean, the reason the scattered light you don't see further out is also just because it's temperature, right?
Yeah,
it's cold in the outer disk. So if you're looking at scattered light, right, there's just less photons to hit that dust and make it glow, even if it's still there.
You're right.
Avery?
Could you go back to the slide with the degeneracy for Abia-Auriga, degeneracy between alpha and disk mass?
Yes.
Yeah. Can I interpret the horizontal line here as like a Q equals 1 type line? Or?
This line here.
Yeah.
So yeah, it is that here the disk to star mass ratio below this line would be too small to have gravitational instability for this system. So yeah, we expect for sure that this mass is higher.
Okay, so I guess if I were to argue that this disk is self-regulating, would I then interpret alpha as like 3 on this plot, or if I said this disk was self-regulated, then it's close to like the boundary between gravitationally unstable and not, right?
Okay. I mean, this is not exactly a Q equal 1 threshold. So this is just let's say we expect the disk to be more massive than 10% of the star to have such spiral arms. So it's not a Q equal a constant Q line in this space. So it's not like it is. This is just, I think, just a curve we plotted for reference. So we expect to be higher. Yeah.
Can you place any constraints?
That's a good point.
By assuming some Q.
I'm not sure we have a good temperature estimate, but in that case, it would be possible to place a bit more constraints, yeah.
Much, yes.
So sorry if you have already mentioned this before, but can the spiral arms increase or decrease the rate of angular momentum transport?
Yeah, so the idea is that the spiral arms are really driving the transport of angular momentum here. So they are like giving a radial velocity to the particles, to the gas particles, and so they're basically making them migrate inwards.
So how does the spiral arm driven transport compare with the viscosity transport?
Yeah, so the idea is that for young disks, for young unstable disks, we expect that the angular moment, the reason why angular momentum is transported are the spirals, so is gravitational instability, and within, like, if we suppose that the disk is unstable, the alpha we can generate with the GI usually is enough to explain the accretion we observe. Of course, the problem remains because we know that evolved disks are not unstable, but the angular momentum is still transported there. And so then we don't know, like for evolved disk, what is the main driver. But for young disks, gravitational instability may be a driver for it. Yeah.
I have a couple of questions which might or might not be related. The first is, can the spiral, it's in the later part of the talk, can the spiral arms transport angular momentum across the inner Lindblad resonance? And the second question is, in the last simulation that you showed, there's an evacuated zone around the central star, and I'm wondering if that, what phenomenon that it is due to, or
Like here, this, let's say, this inner part, you mean?
yeah, and then in the very last simulation, the one that you said was shown on,
Okay, yeah, I see, okay.
was on the laptop.
So
Here the spiral arm goes across the inner Lindblad resonance.
yeah, here they go across. And honestly, in this work, we haven't really studied the transport of angular momentum in this kind of disks. And actually, I'm very keen on doing it. So for this, I will let you know. And as for the evacuated region around the central star, this is a numerical artifact of SPH. So we really don't trust much what is happening close to the inner boundary. And yeah, depends on the finite resolution of the simulation.
Yes, at the beginning, when you were defining this alpha parameter, you said it depends on the density contrast. So I think it also depends on the density profile. So I'm assuming that the steeper the density profile, then you're transporting angular momentum more efficiently.
So the idea here is so there I define the alpha generated just by the spiral, and for just a spiral, what is determining the quantity of angular momentum that is transported is how the amplitude of the spiral. But if we go back to this, let me show you to the equation where I define the alpha. So okay. Here we see alpha, I mean, alpha is just a number, and here we do not assume that it varies radially, it's just a number for the disk. But of course, like you see, the kinematic viscosity depends on the radius, because it depends on the surface density and depends also on the hydrostatic height. So there is for sure a modulation of this kinematic viscosity as a function of radius. But alpha itself, we interpret it as just a constant number throughout the disk. This is not for necessarily true.
Yeah, because I was wondering if there's like a particular slope, for example, for the density profile where the angular momentum is sufficiently been transported. Just by the density contrast, let's say.
No. I mean, this is density contrast for the spiral. This is just valid if you have a spiral as pattern. Yeah.
All right, so yeah, keep going. I want to say this was a wonderful talk. Thank you very much.
Thank you very much.
And it so happens that we, in group meeting, we just had a discussion on the nature of spiral structure in disk galaxies. So we're perfectly, everybody who's here from my group is perfectly primed. So I have a question actually about the slide you were showing where there was the evacuation at co-rotation.
Yeah.
And you were saying that
K is imaginary in that zone.
Yeah.
And I'm just wondering what's driving that. Do you have insight into?
Yeah. So in this case, the reason why we have the imaginary K, okay, is due to the Umri parameter profile. So the correlation here is the injection radius. So we are injecting particles there. Okay. And so the idea is that right outside of the injection radius, the Umri parameter has a little bump, so it's a little bit higher than 1, and that's why we have this evacuated region.
All right, well, I think we are at time. Thank you for being perfectly on time, and let's thank Cristiano again. Come see him again, but not in this.